Section 3. Approximations, limiting cases. Considering limiting cases, or sometimes, or also known as special cases, first of all, they can be really helpful when you're starting a problem. Because let's say you don't really know how to approach a problem. If you consider, okay, what if I made this length really, really big or really, really small? What would happen? Or what if I made this angle, I don't know, 360 degrees or 0 or something? Then what would happen, right? Like, oh, okay. So it helps you kind of start a problem sometimes. And then so that is the benefit of using limiting cases at the beginning of doing a problem. But you should always use limiting cases at the end of a problem. Once you've got your answers, similar to how you would use dimensional analysis, you make sure the dimensions all work out. They do, great. So you're not definitely wrong. Then you apply limiting cases, and you see like what happens when I put this to 0, or when I make these two things equal to each other, or put this to infinity. You see, like you already know what is going to happen based off of your intuition. And based off of that, you see like, okay, yeah, the equation becomes this. And so it matches my intuition about what would actually happen, right? So again, it's an indicator that you aren't definitely wrong. Okay, again, you might not be right, but at least like, okay, I can move on, like this is the best I can do, you know what I mean? So, all right, so we're gonna work through a couple of examples. So here's an example. Dropped ball. Yeah, so this is not really an example where it's like there's like a solution necessarily at the end. We're just gonna like analyze this system with limiting cases, right? So, we have a beach ball, and it's dropped from rest at height h. Okay? So say height h. Okay, so it's just dropped from rest at height h. Okay? H. And it's just dropped like this, right? And so from rest meaning this, right? And we have G. So now we're going to assume that the drag force from the air, so there's air resistance happening, right? We're going to assume that it takes this form. Mass of the ball times alpha, some constant, times the velocity. It's a weird V. Okay, we don't have to solve this right now. We'll find later in chapter 3 that the ball's velocity with time is going to equal this: minus g over alpha times 1 minus e to the minus alpha t. Okay, and it's the ball's position, the ball's height, essentially, is going to be h minus g over alpha times t minus 1 over alpha times 1 minus e to the minus alpha t. So now we want to use limiting cases to see if this answer has the potential to be right. So let's think of the situation where t is really small. And I'll say specifically alpha t. When this number is really small, we can use Taylor series to approximate e to the minus alpha t, right? Because e to the minus x is 1 approximately equal to 1 minus x plus x squared over 2. Right? And there's more terms, but since this is really small, we can pretty much just stop there. So now, putting in alpha t for x and substituting these three terms in for e, we'll look at v of t. Okay? So now v of t is this, minus g over alpha, and then 1 minus, and then 1 minus x plus, not x, but alpha t plus alpha t squared over 2. Okay? And then this is going to be minus g over alpha. And then you have 1 minus 1 plus alpha t minus alpha t squared over 2. Minus g over alpha. 0 alpha t minus alpha t squared over 2. Now remember, alpha t is really small, so we'll not even be we don't even have to worry about alpha t squared is super small, so we can say that that's 0. And so alpha times alpha, this is just minus gt. Does that seem right? Well, that's what it is in free fall, isn't it? So this is like if alpha is really small, then the force is really small. Okay? If t is really small, then there isn't enough time for the drag force to really be involved, right? To really get involved. And notice, by the way, we couldn't just set alpha equal to 0, because then this will go to infinity and it won't help us, right? So that's why we needed to use the Taylor series expansion. So now let's examine y of t. Okay, again, we can't just say that alpha is 0. So we'll have to expand e to the minus alpha t. Okay? So we have y of t equals h minus g over alpha times t minus 1 over alpha times 1 minus alpha t plus alpha t squared over 2. Okay. So this is going to be h minus g over alpha times t minus 1 over alpha times 1 minus 1 plus alpha t minus alpha t squared over 2. Okay. H minus g over alpha t minus 1 over alpha. 1 minus 1 is 0. So we have alpha t minus, I'll do alpha squared t squared over 2. H minus g over alpha times t minus, this is just t, and then plus alpha squared over alpha is alpha t squared over 2. This is going to be g over alpha times alpha t squared over 2. And then we have alpha and alpha, so g t squared over 2. All right. So this is position, right? The height of the ball. And by the way, this should be h, not h bar. But so notice that this gives us even more confidence that we're right? Because it reinforces what we got for velocity. Because it also shows that for small t and small alpha, we that this ball should experience free fall, right? Because the drag force is small and the time is small, so there's not enough time for the drag force to get involved, right? So there you go. So now, cool. So we said, okay, what if alpha t is really small? But what about when alpha t is really big? Okay, so let's take a look at v of t, right? So basically what's going to happen is, if this is really big, this is going to be e to the minus infinity, which is, 1 over e to the infinity, which is like 1 over infinity, which is 0, right? So this term is going to vanish, and we're left with negative g over alpha, right? So negative g over alpha for t really, really big. Now, does this make sense? Well, it would actually make sense because this value is actually the terminal velocity. And you can see that because what happens when an object is falling and experiences air resistance, right? What happens eventually is that the force, the gravitational force balances out with the drag force, right? So in other words, the net force, so the acceleration becomes 0, the velocity becomes constant, it becomes this terminal velocity. So what happens is the net force becomes 0, right? The net force being negative mg plus fd, okay? So fd will become mg. And what's fd? Fd is negative m alpha v so m's are gone, and we see that v is negative g over alpha. So this is the terminal velocity. So we get what we would expect there. Now let's take a look at what happens when alpha t is really large for the position. Again, this term goes to 0. So what are we left with? We're left with h minus gt over alpha plus g over alpha squared. So in this case, I don't think that it would help us necessarily, because it's not like our intuition, or at least not my intuition doesn't tell me that when time gets really long, or when the drag force becomes really strong, that the position becomes this. But it's generally a really good idea. Notice that alpha t is a dimensionless quantity. You can gather that, right, by noting that it's being subtracted here, right, by a number, or that it's used in an exponent. So in general, we play around with dimensionless quantities when it comes to exploring limiting cases. And that's just because we don't necessarily know, beforehand, what the system, what characterizes the system. So like we don't necessarily know if what constitutes as a small or large time, because if it's like a quantum system or like a nuclear reaction, something like that, then time could be of like, I don't know, a millionth of a second or whatever, like a typical characteristic time. But when it comes to a supernova explosion, time then would be like millennia, right? Like characteristic time. So that's why we just go with dimensionless quantities. So how did we know where to stop in our Taylor series, right? So notice that when we were looking at alpha t very small and looking at v, we didn't need this term, right? And then when we were looking at the terminal velocity, we did. So how did we know that we needed this? Well, the idea is you just kind of check, right? You put in a couple terms, one like two, like this many is usually a good amount, right? You put that in, and then you see what happens, and we see like, okay, I could include alpha t squared over 2, and if I did, I'd get minus gt plus g alpha t squared over 2, but I don't know what that's all about, what that term is all about, but I noticed that if I get rid of it, I have minus gt, and this is, I know about this. I know about minus gt, right? So that's the idea, is that you try a few and see what happens. And then if suppose we got rid of the alpha t squared term in the next v, right? Or even in this position, right? If we got rid of the alpha t squared, what would happen? We'd have t minus t is 0. We'd have h minus 0. And then you'd have that the position is h for a really small time. And like, yeah, we knew that already. I mean, it's not as illuminating. But when you see gt squared over 2, you're like, oh yeah, you know what? That's free fall. So my point is, if you don't include that many terms and you get something like just trivial, you should go back and add in a term. All right, so now let's do some more examples. So here's another example. two masses in one dimension. So we have a mass m and with speed v. And it approaches a stationary mass, big M. Okay, it's bigger. All right, so a mass m traveling at speed v approaches a stationary mass m, big M. The masses collide elastically, and all the motion is confined to one dimension. The final velocities of the particles, and we'll see this. We'll see how to get this in chapter 5. But for now, just take for granted that the final velocities. So the final velocity after the collision is v little m. Is going to be little m minus big M times v over big M plus, little m plus big M. And then the velocity of big M is twice mv over small plus big, okay? So, what are the special cases that are begging to be checked? So the first one is going to be when the two masses have the same mass, when the two objects have the same mass, okay? So what happens here? Well, okay, conceptually what do you think is going to happen, right? If the collision is perfectly elastic, okay, that means all of the kinetic energy is conserved. All of the kinetic energy from this mass is going to be transferred into this mass when they collide, like a cue ball, right, in billiards. And then does that happen? Well, when they're equal, this goes to 0. That tracks, right? And then if this is that, then I'll say that v little m goes to 0, and v big M is 2mv over 2m. That tracks too. So in other words, this mass will acquire this v, right? Okay, what are the other limiting cases? What about big M much greater than little m? What do you expect? You expect this guy to not really move, not to acquire any velocity, right? And this to just hit it and come back like a wall. So does that happen? So in that case, v little m, I'll write over here. So when big M is much greater than little m, what happens? Well, the difference now, this is basically 0 compared to big M, right? So that's just big M, v, and then this is basically just big. This is basically, when you add them, this is basically 0. So this is also just basically big M. So I'll write v little m. And that is v, right? That also tracks. Maybe with a negative sign, right? Because 0 minus big M is negative big M. So that makes sense because now it's basically just going in the opposite direction. Okay. What happens to the mass of big M? Well, look, this again is like basically 0. So we have 2mv, and but remember, this is so small and this is so large that this is basically going to be 0, right? Because this is going to go to infinity. And this is going to go to 0, right? So this is basically 0. So it won't really move. Okay, and the final limiting case is the opposite, right? What happens when little m is much bigger than big M? Well, what do you expect? Little m is going to be so massive, it's basically just going to run over big M. And it's not really going to be phased by big M. It's going to basically it should have the same velocity as before, right? And then, I don't know, what's going to happen to big M? I'm not really sure. So let's see. If little m is much greater than big M, then this factor, big M is basically 0, so that's going to be little m times v. So this is v little m times v, like that, and this is going to be over basically little m, right? And that is v, which makes sense. It didn't really get phased, right, by this by big M, right? So just draw it. Little m, and then here's big M. So, and then now let's see what happens to big M. So v big M, what happens? Well, 2mv, that can stay, and then this is basically little m, right? So little m, so somehow it acquires twice the velocity. Okay, didn't really expect that, but that's the neat thing about limiting cases. One of the neat things is that sometimes you discover new things too. It's not just about checking your answer, but it's also learning about your answer, assuming it's right? All right, let's do another example. A mass is suspended from a weightless string, something like this. Weightless string of length L, set into motion such that it moves in a horizontal circle. Oh, so it's more like, it's not like this, but it's more like, so it's going like this, right? The string maintains a constant angle, theta, with the vertical. We're going to find out that the angular frequency of this motion, okay, that means like how many revolutions per unit time, is equal to this. So now let's examine some limiting cases by playing around with theta. There's basically two limits, and this is a dimensionless quantity, right, theta, so we can play around with it directly. Okay, and by the way, you might be wondering, in the last example, it wasn't a dimensionless quantity. Yeah, but you're comparing apples to apples, so it's fine, right? When you're comparing two different masses, that's fine. But it's basically this, it is a dimensionless quantity. You're playing around with this, right? And checking that if this, stuff like that, right? So this too is a dimensionless quantity, so we can mess around with that. So what are some limiting cases? Well, what if theta went to 90 degrees, right? What if you're dealing with something like this? If a cosine, so cosine of 90 is 0, right? Which means that omega would go to infinity. I think that makes sense. Your pendulum would look like that, and your circle would look like this, right? And in order for this to never flop down, you'd have to spin it infinitely fast. What if theta went to 0? Then what does this make? This makes 1. So your omega would be square root of g over L. Okay. So what would you'd be left with this, wouldn't you? And guess what? This is your standard plane pendulum, right? That simply swings in a plane. Okay, so now we're ready to move on to problems. So let's do problem 1.6. Projectile distance. Okay, so a person throws a ball with an initial speed v from the edge of a cliff of height h. Selecting the angle to achieve the maximum possible horizontal distance. Among the following expressions, okay, so there's these expressions, determine which ones represent the maximum horizontal distance traveled by the ball. Don't solve the problem from scratch, just check special cases. So why don't you go ahead and pause the video here, attempt this problem on your own, and then I'll provide a hint if you get stuck. Okay, so now here's the hint. So what I suggest is to examine the following limits, okay? When h goes to 0, what do you expect? Okay, what do you expect? You don't have to think about a mathematical expression for the distance, but what do you expect conceptually if h goes to 0? Okay, do you expect that the distance goes to 0 or to infinity or maybe some finite number, some finite value? Okay, what happens when h goes to infinity? What happens when v goes to 0? Conceptually, of course. What happens when v goes to infinity? You could even think about what happens when g goes to 0. What happens if there's no gravity? And what happens when g goes to infinity? Okay, so think of these three things, and then this is still not quite enough, in my opinion. When you encounter a rational function, we like to see, well, what happens when the denominator is equal to 0? So look at that too. So that's your hint, okay? All right, so go ahead and pause the video if that hint helped. Otherwise, let's take a look at the walkthrough. So here's our choices. V squared over G. V squared H over G. 4 is going to be v squared over g times the square root of 1 plus 2gh over v squared v squared over g times 1 plus twice gh over v squared and v squared over g times 1 minus twice gh over v squared. Okay? All right. Now, what do we expect when h goes to 0? When there's no height at all. Okay, so here's a picture of what's happening. They're right here on the cliff, right? And they're throwing a ball. Okay? And here's the distance that we're trying to obtain here, okay? What? And they throw it at an angle, okay? That's important, okay? Do we think that if there's no height at all, if you throw it at an angle, you're still going to get some distance, right? So if h goes to 0, that doesn't mean so that our distance will go to 0, okay? So we can eliminate this one. And now what do we have? We have v squared over g. It shouldn't depend on h, right? When h goes to infinity, we would expect that the distance goes to infinity. So we can eliminate that one. How about this one? Again, we have the same issue. When h goes to 0, we have 0. All right. How about this one? When h goes to 0, we do not have 0. Okay. And let's see here. What about when h goes to infinity? Well, let's rewrite this. Maybe this goes to, does this go to infinity? So what I can do is I could divide by v, right? Divide the outside by v and multiply the inside by v squared. Okay, this gives us this, right? V over g times square root of v squared plus twice gh. So when h goes to infinity, this term becomes the dominating term. And then this goes to infinity, right? So that seems fine. Okay. I mean, the point is that that it goes up with h, right? All right. What about when v goes to 0? So we'll look at this here. Yeah. So we would expect the distance to be 0 completely, right? If there's no initial velocity. Well, that seems to be the case. This term would go to 0, and it would multiply. So if if v goes to 0, then it would be about, well, it would be 0 times anything is 0, but this term would be like that. And then 0 times anything is 0, right? So that is aligned with our intuition. What about when v goes to infinity? We would expect the distance to go to infinity, right? So, I mean, that seems to be the case. When v goes to infinity, you'd have this would be the dominating term. Right, so v over g times the square root of v squared. This is going to be v times v over g. This would go to infinity, right? So that lines up with our intuition. What about when the gravity is so small that it's 0? You would also expect an infinite distance, right? Because it would just go up and up and up and up. So, does that, when g goes to 0, is that okay? Does that make sense? So we have that this term would go to 0, right? So we have v over g times the square root of v squared. And then this would go to 0, and so that would go to infinity. So that lines up. What about when g goes to infinity? Okay. When g goes to infinity, what do we have? What are we working with? We have that this term dominates, so v over g times the square root of v squared. That term this term dominates, so twice gh. This term overpowers this term, so this would go to 0. That makes sense because the gravity would be so heavy that you wouldn't be able to throw the ball at all, right? It would take infinite amount of energy. So that makes sense. Okay. And is this a rational function? No. Right? So we don't have to worry about that. So I want to keep this on the back burner, and let's move on. Okay, what about when h goes to 0 here? What's happening here? When h goes to 0, we have v squared over g, and then just 1. Okay, that is fine. I'm cool. I'm all right with that. What about when h goes to infinity? What do we have? We have v squared. This becomes the dominating term, so v squared over g times 2gh over v squared. V squared and v squared. G and g. And it goes to infinity, so I don't see what's wrong with that. V goes to 0. Is there anything wrong with that? So if v goes to 0, what happens here? This becomes the dominating term. Right? So you're left with this. And then maybe this happens, and this happens. When v goes to 0, we're left with 2h. Yeah, I'm not a huge fan of that. Because it should go to 0, right? So I want to erase this one. I want to eliminate this one as an option. What happens when v goes to infinity? This, yeah, okay, that works. That the distance goes to infinity. When g goes to 0, we're left with infinity. That's good. And then when g goes to infinity, oh, I'm not a huge fan of that either. When g goes to infinity, what happens? So what happened over here when g went to infinity? When g went to infinity here, this dominated. Yeah, this term dominated, right? But now that's not necessarily the case here, right? So when g goes to infinity, what happens? This term dominates. So we're left with v squared over g times twice gh over v squared. Twice gh over v squared. Okay, v squared, g and g. Okay, we're left with 2h again. When g goes to infinity, actually it should be 0, shouldn't it? So I'm not a big fan of this one. I'm gonna eliminate that one. Okay. Let's see what's going on with this last one here. Oh, well, we have a rational function, right? Let's just look at all the things, though. So we have when h goes to 0, what do we have? This is simply v squared over G. That's fine. I'm okay with that. Actually, I like that. And then what about when h goes to infinity? Then we have v squared over g times kind of this negative twice gh over v squared thing going on. And I don't really like that. Well, we have a negative sign, v squared over g. And then we have a v squared on top. So v to the fourth. And a 2gh on the bottom. 2gh. I don't know, we have a negative value. So I'm not... Why would the ball go backwards if the height goes to infinity? I'm not a huge fan of that. What about when v goes to 0? Right, so v, so okay, so when v goes to 0, this term dominates. Yeah, it's kind of the same situation. When v goes to infinity, this term goes to 0. So we have v squared over g, and that goes to infinity. That's fine. What about when g goes to 0? Yeah, that's weird. So this term vanishes, and then this goes to 0. No, that's not that weird. This goes to infinity, and that's fine. I'm fine with that. What about when g goes to infinity? This term dominates. So okay, so when g goes to infinity, we have v squared over g times, and this term dominates, right? So negative twice gh over v squared. This makes negative v squared with another one over twice g squared h. So g is going to infinity. This kind of goes to 0, doesn't it? Yeah, that makes sense. Okay, so that's fine. But we weren't really a fan, right, of this stuff going on. Now, well, let's think about this. What would happen when the denominator... What would happen when we set the denominator equal to 0? Okay, so this should go to infinity, right? So when the denominator equals 0... we have 1 minus twice gh over v squared equals 0. Then we have 1 equals twice gh over v squared. It looks like v squared equals twice gh. What this means is that if our v squared, if our v is the square root of twice gh, if we throw this at an exact velocity of square root of twice gh, this blows up to infinity, which doesn't happen, right? It just doesn't happen. So I'm going to go ahead and say that number 4 here, the equation number 4 is the correct answer. So now we have exercise. Exercise 1.13, Atwood's machine. Okay. Consider the Atwood's machine shown, which consists of 3 masses and frictionless pulleys. So it looks like this. Okay, you can't see the image, but I'll draw the image. Okay. Looks like this. Okay. So, the acceleration of m1. So the acceleration of m1, okay, is given by this. 3 m2 m3 minus m1 4 m3 plus m2 all over m2 m3 plus m1 4 m3 plus m2. Okay, with upward taken to be positive. Okay, find a1 in the following special cases. Okay, so let's see what happens now when m2 is twice m1, which is twice m3. All right, so go ahead and pause the video, try this on your own. Okay, now I'll give a hint, and my hint, the math is pretty straightforward, so just put m2 over 2 for m1 and m2 over 2 for m3, okay, and just see what you get. Now, before you do that, I want to give you a hint about the concept that's happening. This mass is trying to is pulling this down, which will try to pull this up, and likewise, this mass will also try to pull this up, right? So if m2 were to be double m1 and m3, that would be just enough, maybe, to cancel out what's happening here. So use that as your prediction for what's going to happen. Okay, A1 equals G3, M2 is still M2. So now, so M3 is now half of M2, right? M3 is half of M2. So M2 over 2 minus M1 is half of M2, right? M2. And then 4, and then half of M2 plus M2. So, right, so conceptually, what's happening here is that this mass is twice these two, right? So we want to know what would happen to the acceleration of 1. Is it going to go up, down? You know, just predicting, just conceptually, if this thing is so heavy, I think it would bring these two up, wouldn't it? Along with M, right? So G, so plus 2, M2, right? Okay, now over. So M2 is still M2, and then M3 is M2 over 2. Okay, and then plus M2 over 2 times 4 times M2 over 2 plus M2. Okay, and now A1 is, let's see, so we have, would M really be squared? Maybe if it gets divided by M squared, yeah, sure. Because it's, yeah, we have a G, right? So 3, looks like we have 3 halves. And G is still here, so I'll keep the G, right? G, and then 3 halves, right? 3 halves M2 squared minus, this becomes 2. Okay. And then I'll just keep it, just to keep things organized. So minus M2 over 2, right? 2M2 plus M2, okay? And then this becomes M2 squared over 2 plus, I'll keep this M2 over 2, right? And then I'll just do, this is 2, okay? So 2M2 plus M2, okay? Let's keep simplifying. So now this is still 3 halves, M2 squared minus, okay, M2 over 2, and then this makes 3M2. Okay, over M2 squared over 2 plus this is M2 squared, or over 2. And this is also 3m2. 3m2, okay? Now, this is 3 halves m2 squared minus 3 halves m2 squared. 3 halves m2 squared. And I'm not sure I care about what happens here, because this is 0, right? So what happens, actually? This becomes 3m2 squared, and then 3 halves plus another half makes 4 halves, but it doesn't matter because this is 0. The acceleration is 0. So our prediction didn't happen, right? But oh, that actually, okay, that does make sense, because if this is twice the mass of both of these, then it kind of makes sense because it's balancing out, right? This is actually static equilibrium, right? So, if this is twice, then you can think of it like this M1 is trying to pull this up, this M3 is trying to pull this up, but because this is twice the mass of these two, it's gonna pull it back down. So it's gonna be sufficient enough to pull these back down. That's pretty much what's happening. All right, so now suppose that M1 is much larger than M2 and M3. So I'll let you try this on your own, see what happens. So now I'll provide a hint for part B. So what you want to understand is that the product between M2 and M3, when compared with M1, should be really, really small. And although this M1 is being multiplied by the sum of M3 and M2, which is really small, I still think that the product between M1 and this sum is so much bigger than this product that this product basically vanishes when being added or subtracted by this term. Okay, so that's your hint. Now I'll walk us through the solution. So what I'm thinking is if M1 is much bigger than the other two, right? Doesn't it make sense that the acceleration would just go down? And just kind of these two would be negligible, right? So what I'm thinking is that it would just go down and free fall, right? So just G. So let's see what happens. So A1, so I think A1 should just be G, right? So if M1 is much bigger than M2 and much bigger than M3, okay? So we have 3 M2, M1, M2, M3. This is a really small number, right? This number is going to be really small because we're going to compare it with this, which is much bigger, right? This number is going to be really small as well compared to this number. Okay. So what I'm thinking is these terms basically vanish. And we're left with negative M1 times 4 M3 plus M2 over positive M1 times 4 M3 plus M2 and times G. And this is negative 1. So this is negative G, right? So that's exactly what we thought. Now we have part C. M1 is much smaller than both M2. So the opposite, right, of what we just encountered. All right, so I'll let you try that one on your own. All right, so now I'll provide a hint for part C. It's kind of like part B, but the other term will be the one to stick around, right? And these will be the ones to vanish. And now I'll provide a walkthrough. So let's see, what do we predict here? If M1 is much smaller than M2 and M3, going back to our drawing, this is just gonna ride up, right? It's gonna ride up by M2 and M3. So it's going to probably, it's going to be not necessarily positive G, but definitely a positive value that that's probably bigger than G, right? Because it's going to accelerate due to the two combined masses, right? All right, so we have G, and then, so M1 is much smaller than M2 and M3, right? So now this product can stay when you compare it with the other term. And likewise, this product can stay. So yeah, and then of course these terms divide into 1, so we have 3g. And that makes sense. It's an upward velocity bigger than g, just like we thought. All right, now part D. M2 is much bigger than M1 and M3, which is equal to M3, okay? All right, so I'll let you try that on your own. So for your hint, this term is negligibly small compared to M1, so it's basically just going to vanish, okay? So think of it like that. All right, so now let's do a walkthrough of D. So let's go to our prediction conceptually, right? M2 is much bigger than M1. All right, so this is going to just skyrocket up. So what I'm thinking is that this will probably just fall at, or this will cause like M1 to accelerate at G. That's my prediction. Because basically you just have this, it's almost like this object is just free falling. I mean, it's not, but it's going to be pulling these up at G, right? It's almost like it's free falling. A1 is G, and then 3, and then I'll keep M2, right? And then for M3, I'll just write M1, let's say, minus M1 times 4M1 plus M2 over M2 times M1 plus M1 times 4M1 plus M2. Okay. Now what? Now, so M2 is much bigger than M1. So even if you multiply M1 by 4, the dominating term is going to be M2. Right, so let's do that. Let's say this is M1, right? And so this is just basically M2. Okay, let's just write M2. M2, right? So 4M1 plus M2. Yeah. And then down here, we'll keep this M2, M1 plus M1. And here, it's basically just M2 again. Yeah. Well, okay. So this is going to be G, and then 3 times this product minus this product is 2. So 2 M1, M2. And then this is also 2 M1, M2. So it's exactly as we predicted. It's just going to go up at an acceleration of G. Okay, part E. M1 equals M2. So now all the masses are the same. Okay, so I'll let you try this one. I'm not really going to provide a hint for this one. It's pretty straightforward. Conceptually, I didn't expect what's going to happen here. So, and I don't expect you to. So I believe that this one is to provide insight on what would happen in this limiting case rather than to be used to check your answer. And now I'll provide a walkthrough. So now we have M1, M2, and M3 are all the same, right? So what I think would happen is what would happen to A1? Well, I do think that M1 will M2 will try to pull this down, right? And pull this up. M3 will try to pull this up, which will contribute to this being pulled down, right? So I think it'll go up by maybe 2G or something like that, right? So let's see. So A1, and we'll just write M1 for everything, right? So A1 is G M1 minus M1 times 4 M1 plus M1 over M1 times M1 plus M1 times 4 M1 plus M1, okay? This is going to be 3M1 squared minus M1 times 5M1 over M1 squared plus M1 times also 5M1, okay? Now what do we have? Now, this is 3M1 squared minus 5M1 squared, 5M1 squared over M1 squared plus 5M1 squared. So I have 3 minus 5 is minus 2 M1 squared over 6M1 squared. That's minus G over 3. So it's not what I predicted at all. So, you know, sometimes limiting cases, instead of us predicting what's going to happen, sometimes limiting cases are there to give you new insight, right? So, now, we'll try this exercise. (1.16) projectile with drag. Okay, a projectile is subjected to a drag force. Is launched with an initial speed v initial at an angle theta. The height as a function of time is given by this equation. Okay, demonstrate that in the limit of small alpha. Okay. This expression reduces to the standard projectile motion equation. Okay, so if alpha is much less than 1, or I should say if alpha t is much less than 1, right? Show y of t equals v naught sine theta t minus gt squared over 2. All right, so I'll let you try this one on your own, and then I'll provide a hint. Okay, so my hint for this is to use Taylor series. Okay, So this is what they mean. This answers the second part of the question. This is what they mean by small alpha. What they mean is alpha t is much less than 1, right? Because there's no such thing as small alpha. It needs to be a dimensionless quantity when this is much less than 1. E to the minus alpha t. E to the minus alpha t is 1 minus alpha t plus alpha squared t squared over 4. No, over 2. Y of t is 1 over alpha, and then v naught sine theta plus g over alpha, and then times 1 minus alpha t plus alpha squared t squared over 2. Minus gt over 2, right? gt over 2. gt over alpha. Yeah, okay. gt over alpha. So, okay. So let's do that then. Let's see what happens here. My concern is that I don't see how this alpha is going to go away. So, okay, 1 minus 1 plus alpha t minus alpha squared t squared over 2. I wonder if do I need this term? Maybe not. This minus gt over alpha is a separate thing. This is all one term, and this is the second one. So this is all one term, right? Yeah. And then this is a second term, okay? Now, reduce this, or simplify this, by just writing 0 here. So alpha t minus alpha squared t squared over 2 minus gt over alpha. Why don't we take this 1 over alpha and multiply it by these two terms? Oh, yeah, okay. So this is v naught sine theta plus, this makes t, and then minus alpha t squared over 2 minus gt over alpha. Right, so now we could expand this guy. Right, so that's going to be v naught sine theta t, this whole thing times t, gt over alpha. And then this whole thing minus this term times negative this term, right? So v naught sine theta alpha t squared over 2. And then minus alpha, or I'll just write g over alpha t squared over 2. And then minus gt over alpha, okay? So this will stay. We want that term to stay. Okay, gt over alpha minus gt over alpha, okay? We want this. This is this, right? And then minus v naught sine theta alpha t squared over 2. But this term is so small that it goes to 0. All right, well, I really hope that you enjoyed this episode of this lecture series. If you did, you can drop a like. It means a lot. If you're interested in following the series, you can subscribe to the channel. That's always dope. If you have any questions, do not hesitate to comment. I will answer your question in a timely manner. If you think you might benefit from my tutoring services, go ahead and email me or scan the QR code right there on the screen to set up a 15-minute consultation with me. We could go over things like, discounts, exactly what subjects I teach, or honestly, if you just feel like you just need 15 minutes of tutoring, there's your free 15 minutes. I could help you maybe solve a physics problem or something like that. And yeah, with that, peace out.